Welcome back, everyone. In the previous lecture, we went ahead and read in the data, pre-processed it, and then we trained our model. Let's go ahead and evaluate our model. I'm going to head back to that Jupyter notebook where we left off last time. All right, we just trained our model. Let's go ahead and read in those metrics or those losses based off the model history by saying pd.dataframe and call it on model history.history. And what we're going to do here is we could just check out the metrics themselves by running it as such, but it's probably more interesting to plot them out. Let's say metrics. Let's call the columns real quick to save ourselves a little bit of typing. We'll say metrics on, and let's go ahead and we can grab all of them and then just delete some of these. So we'll paste that in and we'll compare accuracy versus validation accuracy. And let's go ahead and plot that out. Okay, so it looks like the training accuracy continues to rise and the validation accuracy, it looks like it was also continuing to go up a little bit, flattening out. But remember, we indicated that we wanted to stop based off the loss. So that's probably going to be more informative of why we stopped training early. So we'll say loss compared to validation loss. Go ahead and plot that out. And here's a really indicative chart. So we can see the training loss is going down, but we weren't getting any improvement on the validation loss. And in fact, it looks like it was starting to go up. So probably a good idea to start ending training at around 7 epochs. As always, we can get the final evaluation metrics either by just looking at this last row in our data frame, or by saying model evaluate, and we could evaluate on X test, Y cat test, say verbose is equal to 0, so you don't see a big printing output. And if you run that, it basically shows you back the same results. So 0.985, come back up here, notice 0.985, and then you have 0.69, and there's 0.69. So same results that are in the actual history. Let's create a classification report and confusion matrix to further evaluate this. sklearn metrics, import classification report, confusion matrix. Let's actually get our predictions. So that's model predict classes off X test. And then we'll print out a classification report comparing our true known values from Y test. In this case, we don't pass in the categorical, we just need the actual numbers, versus our predictions. Print that out, and we can see our precision, recall, and F1 score, as well as our overall accuracy. So the things we want to think about is how good of an accuracy is 69% accuracy? Well, the first thing you should compare it to is just random guessing. And because we have 10 classes here, a random guess has a 10% chance of being correct. So we're getting 69% accuracy overall, which means our model is actually performing quite well given the circumstances. And here, what's really nice about this classification report is I can take a look at what classes it's actually not performing that well on. And you can see it tends to perform poorly on class number 3. And we can take a look at this and see 0, 1, 2, 3. So it looks like it has trouble with cats. And if we take a look at, if we have 3 here, that's 4, 5, we have dogs. Take a look back here, you'll also notice it doesn't do that great on dogs. And in fact, they perform very similar to each other. And that's because when you blur an image so much that it's only 32 by 32, cats and dogs can look really similar to a computer. So we actually would expect it to perform quite poorly here. You can see it performs quite well on class number 1, which is an automobile, which is probably the most distinctive out of all these. However, you should notice there's also trucks. So the fact that it can perform automobiles so well, given that there's already a truck category, which is quite similar to automobiles, is pretty impressive. So we'll come back here. The other thing we can do, as before, is kind of view the actual predictions themselves. How many got right, what it's actually misclassifying things as. And as always, you can say import seaborn as SNS, and then say SNS heat map on this confusion matrix. Probably make it a little larger. We'll say PLT figure. Fig size is equal to something like, let's go ahead and say 10 by 6. Run that. And here what's kind of interesting is based off the color, you can quickly see what it's misclassifying things as. So it looks like there is confusion between 3 and 5. And we can get an annotation to see the actual number of misclassifications here. So we can see based off the color, there is confusion between 3 and 5. If we come back here, that was 0, 1, 2, 3, cats versus dogs. So it has trouble with these kind of small furry animals. Makes sense. They're quite similar on a 32 by 32 image. But let's go ahead and see how it performs on just a single image. So if we wanted to predict a single image, we would, just as before, grab a single image. So someone returns back, hey, here's my image data. And recall, this data has already been scaled. So if they gave you a raw image, you'd have to scale it by saying divide by 255. But what I can do here is say PLT, go ahead and show my image. So here's my image. I'm actually not sure what this is. So we'd probably have to say ytest at 0. And that's 3, so that should be a cat. We'll see how well it does. Let's go ahead and say model predict classes. And the thing is, the only thing we have to make sure of is we reshape this correctly. So it's one image, 32 by 32 with 3 color channels. Go ahead and run that, and it looks like it predicted it quite well. So that's kind of surprising because I myself wouldn't be able to predict this. Okay, and I think the one we show in the actual data set or the solutions notebook is image number 16, which is much clearer that it's a dog here. And then we can run that against ytest, which is 16. So that's a dog, predict classes. It also performs correctly. So pretty good performance considering the circumstances here. What we're going to cover next is how to deal with quote unquote real image data. So typically your images, you're not going to be loading them with just a simple keras call. Instead, you're probably going to be loading them from a folder or directory on your computer that has some sort of JPEG or PNG files. In the next lecture, we're going to show you how to download the dataset that we work with, and then the next subsequent lectures will show you how to use Keras built-in image generator and flow from directory functionalities to actually work with real JPEG and PNG files. Thanks, and we'll see you at the next lecture.